Hi, my name is Edward. In this video, I will present the enterprise network design of the Frankfurt branch. Frankfurt branch is part of the TGS global network. It is connected securely to the 7 other branches that have been designed by the other colleagues located across Europe. This presentation will showcase the core design features of the network that adhere to the client requirements through various small demos. One of the core requirements, and the hardest to implement, was redundancy across all the network. Layer 2 and Layer 3 dependencies in this partial mesh network had to be adjusted in order to ensure efficiency. In this test, initially we were connected through IPsec securely to London branch. After shutting down one node from each layer, we will test to ensure that the network will successfully converge to the changes and connectivity is still present. Besides the network devices, the firewalls are configured to ensure high availability as well. The redundancy is more advanced in comparison to the network devices. All the settings configured on the primary firewall are replicated through a dedicated link, so if a failure occurs, the backup firewall can easily take over and maintain the same functionalities. As we can observe from the management PC, we were initially connected to the primary firewall, which is the master node. But since we have shut it down, we have lost the connectivity with it. Now we will log in into the second firewall to ensure that it had took over the primary role. As we can observe in the CARP status widget, the secondary firewall became the master node. The next part is to issue a test to ensure the connectivity to the London branch host is still present. The traffic will traverse all the network layers and enter the firewall encrypted tunnel. In the management PC, we will issue a ping to the London branch host. As we can observe from the replies, the network successfully converged and maintained connectivity. Based on the number of employees, the network requires a total of 34 network devices. Configuring multiple users with different access levels locally on every device is not efficient, hard to implement and maintain. This is why a centralized manner for managing user access to the network devices has been implemented. The TACACS server that we are currently logged in from the management PC is located in the data center and stores all the user access. As we can observe, all the network devices have been configured to communicate with the server. They are placed in groups based on network layer that they belong to. A username administrator has been configured with the highest privilege to be used on all the devices. It is important to set a backup user on each device locally. In the case of a server failure, the backup user can be used to log into the device. Otherwise, if no backup is configured, we could be locked out of the device. Now we will try to test the functionality of the server by remotely connecting from ASW3 to ASW1. After entering the administrator credentials, we have successfully logged in. If we issue a command to check the locally created users, we observe that the backup is the only one, thus the login has been performed by the server. One of the most critical functions within a network is security. Besides Layer 2 and general security measures for network devices to access control lists, traffic filtering on Layer 7 has been enabled as well on the firewall. The intrusion detection system will filter all the traffic going in and out of the firewall and search the database for well-known virus signatures. To test this functionality, we issue a port scan attack from an internal host to the firewall port using Nmap. For the purpose of the demo, and because the attack was performed from an internal host, no blocking is enabled, just the intrusion detection system functionality is checked. After we log into the firewall and check the logs, we observe that the attack has been spotted and alerts have been triggered. By checking the interfaces where packet filtering was enabled, we can see that the blocking is disabled. It can be easily enabled and all the alerts will be blocked, giving the firewall intrusion prevention system capabilities. Besides securely connecting branches through the internet, a solution had to be implemented for the remote employees as well. OpenVPN has been configured on the firewalls. It enables outside, recognized users to internally connect to the branch network on a secure manner. We will test the connectivity from the teleworker located in the remote worker module to the internal network. As we can observe by issuing a command, the host has a public IP address and is directly connected to the Internet ISP. By using the configuration file given by the server in the OpenVPN client, we will try to connect to the branch. The connection is successful and we have been issued a private IP address that is corresponding to the branch network. We can further test it through the command line. Now we will test the connectivity with the marketing department host, and we ensure that the traffic is allowed and correctly routed internally. The connection is successful, as given by the replies. We will try to log in into the firewall now to check the OpenVPN connection. On the dashboard, we immediately observe that the connection is successful and monitored by the server. A network monitoring server has been configured in the data center. All the network devices and the firewall are being constantly monitored. In the left, we can observe that all the VLAN information from the switches is showcased on the server. One of the other functions that the server provides is network management and automation. We can import or download configuration files in a more centralized manner from all the registered devices. Besides, we can execute scripts as well. They can be simple commands or template scripts already made. Let's execute a show version command on this device from the server. Once we check the execution details, we can see that the command was successful and we can gather all the necessary information now. One of the powerful tools that combines both the monitoring and the management functions is an advanced traceroute function. We have created a trace with the destination on one of the London branch hosts. The traceroute offers extensive information about the path that the traffic takes, about the interfaces and nodes involved in the traffic. It makes troubleshooting much more easier. If, for example, there is a bandwidth problem on one of the interfaces monitored, it will be highlighted here and troubleshooting could be performed in order to resolve the issue. Let's showcase that through an example. On the first switch, we can compare the running configuration with the other saved configuration saved on the repository. If any changes were made, they will be highlighted here and the problem could be easily resolved. As we can observe, on the running configuration a change was made. As we scroll down, we can see that the command traffic shape that limits the bandwidth is entered and highlighted. If the change affects the traffic flow, the node can be easily rolled back to its previous working configuration. That was all. Thank you for watching. I hope you enjoyed the video.